I really appreciate the invitation from the SAS Global Journal Club to give me a chance to talk about our synchrotron Thailand and also the technique I'm going to focus today is the XAS absorption spectroscopy. So the outline. Let's see. Okay, so the outline of my talk include some introduction to our synchrotron light source, and its official name is Synchrotron Light Research Institute. And SLRI has a small synchrotron machine. It's only 1.2 GeV electron beam energy, and the Thai name is Siam Photon Source. I'm going to give a detail of the SPS parameter, its operation, and also the synchrotron spectrum produced from this source. And then I will focus on the XAS absorption beamlines. Actually, we have 12 beamlines in operation with several synchrotron-based techniques, and 4 of them are SAS beamlines, and I will give you a detail of the instrumentation, including the beamline optics and the end station or the SAS station. And let's see how productive they are in terms of user utilization and also the publication. And we have to collect a statistic on these 2 factors. And then I will select, I have already selected a few research papers, science papers, that I think they are very interesting in terms of the sample type themselves and also the analytical method they use in those papers. And then I will end my talk to acknowledge the SAS team, a very strong team at SLRI. They are beamline managers and beamline scientists. Okay. So let's go to the first one. Okay, so there are more than 50 synchrotron light sources around the world, but there's only 2 in Southeast Asia, 1 in Singapore and 1 in Thailand. And our synchrotron facility is located in Nakhon Ratchasima province. It is quite far from Bangkok. Here is Bangkok. So by car, it takes about 4 hours now. And unfortunately, we don't have a direct flight from Bangkok to Nakhon Ratchasima yet. Okay, so it's quite difficult for foreigner that land in Bangkok and go to Nakhon Ratchasima. But we have like a transportation service and which facilitated by our user office. So we can do such kind of arrangement, and user can go to our light source easily. And here we are located in the campus of Suranali University of Technology, but we don't have anything to do like we don't govern. We are not governed by the university. So, but we are both mutually benefit from each other because many users come from the university and they have a PhD student and they run their thesis and experiment at our beamline. And here, this is a photograph taken on this side of the road to see the light source building is the round building. It's housing the accelerator and also the storage ring and the beamline. And this is a photograph taken at the front, at the entrance of the building. It's a laboratory and office. Okay, so SLRI is operated under the guidance of Ministry of Higher Education, Science, Research and Innovation. And the Siam Photon Source provides synchrotron lights for both domestic and international user or researcher since 2003. And the number of users keep going up like this. And right now, for the last year, we have nearly 500 users coming all around the country, and also the internal user coming to our light source. And also the number of publication is increasing very rapidly too. And nearly we have, for this year, we have 187 paper published. just half of the year. Okay, and the our synchrotron radiation covers from infrared to hard X-ray energy range. So I will go to detail in the next slide for this 4 insertion device, and also including the spectrum from the bending magnet of the storage ring. And the utilization of our synchrotron light span from basic science, applied science, and also industrial project. And here is the statistic from this year. And as you can see, the major science the research is about material science, and the second category is the applied chemistry and then physics. So this show you the layout of our synchrotron machine. It consists of a thermo-ionic electron gun producing a lot of number of electrons, and then those electrons are queued up and boost up in energy using linear accelerator. There are 2 of them, and each of 20 mega electron volt. So the total energy after booting up the electron is 40 mega electron volt, and then the electron bunches are transported to the booster synchrotron to further increase their energy to 1.2 GeV, and then they got transported to the ground floor. So the accelerator, this part, the electron gun and the accelerator are in the underground floor on this drawing, this building drawing. And then the high energy electron beam 1.2 GeV electron beam got kicked up into the storage ring to circulate in the storage ring, and they are accelerated by the blue magnet and gives the synchrotron radiation to the beamline. So this is a photograph showing the visible light of the synchrotron radiation. Okay, so the Siam Photon Source is considered to be between the 2nd and the 3rd generation light source, because we got it donated from Sortec, Japan, and we have modified the machine and then to have 4 stretch section for insertion devices, and the lattice is the double bend acrobat, and the circumference of the machine is very small. It's only 81 meter, so about 6 meter in diameter. So when you walk around the synchrotron ring, it takes only a few minutes. Okay, so and this graph show you the synchrotron spectrum from the machine. On the bending magnet itself, 1.4 Tesla, you see that it radiates from the radiate photon in the infrared range up to 10 keV. This is hard X-ray, but the flux get lower and lower when you go up in energy. So this is not enough for X-ray technique or some X-ray-based technique. So we use the multipole wiggler. Here is 2.2 Tesla multipole wiggler to increase flux and also extend the X-ray energy to become harder X-ray. And we also have 2 of the wavelength shifter. One is 6.5 Tesla and one is 4 Tesla. And also we have undulator U60 for working on the photo emission spectroscopy and microscopy, because these 2 techniques needs a lot of flux. So U60 can increase flux to order of magnitude compared to the bending magnet. Okay, and we operate the Siam Photon Source 24 hours. Actually, it's 23 hours per day. 1 hour is the injection time. So it's divided into 2 shifts. So we start storing the beam, generate the radiation, the synchrotron radiation from 8 AM, and then we down the beam at 8 PM, and then going to the next period. Okay, and at present the beam lifetime is about 11 hours, and the beam current drops from 150 milliamp to 70 milliamp. Okay, and we have increased the beam time available, and now this year we have about 4,500 hours of beam time available for users. So the beamline at SPS light source here is in operation. There are 12 of them, and we have several techniques like other synchrotron around the world. Here is the X-ray absorption spectroscopy, X-ray diffraction, X-ray powder diffraction, and also X-ray fluorescence analysis. And this beamline, we also have the tomography technique. And this one is the SAC-wax, that is the small angle X-ray scattering and wide angle X-ray scattering. And we also have the photo electron emission spectroscopy and microscopy. And then the infrared absorption spectroscopy beamline, and this can do also infrared imaging. And we also have a deep X-ray lithography, micro X-ray fluorescence, and imaging. And this one is using the using the wavelength shifter, the highest magnetic field of the Wiggler for protein crystallography or macromolecular crystallography. And for my beamline, I'm taking care of beamline number 8. So we have 3 techniques now. The first one is X-ray absorption, and then X-ray fluorescence is about analysis. And then the last one that we have just developed last year is full field X-ray fluorescence imaging. And there are 2 more now in commissioning. One for ASEAN, aim for ASEAN user, and the technique is XAS, and the other is XPS beamline. And this shows the a map of our beamline and the storage ring. And this is the photograph taken in the experimental hall. Okay, and for the beamline number 1.1 using multiple Wiggler, it has three X-ray techniques: XAS, XRD, and XRF. So this beamline has conventional design of the optics. So it has a collimating mirror to make the beam parallel from the diverge beam of the multiple Wiggler. And then the double crystal monochromator selects photon energy or scanning photon energy for SARS. And then the last mirror reduce the beam size to the focusing side on the sample position. And because this beamline use the multiple Wiggler, it can go up in energy range. So it covers from 4 to 18 keV. That means we can study scandium KH up to zirconium KH. And for other heavy elements, we can study them at the L edges and M edges at this beamline, and the photon flux ranging from 10 to the 8 to 10 to the 10 at the end of the spectrum. But however, the beam size is not quite small as expected, and I think the error is come from the slope error of the mirror, and also the alignment problem. So actually we expect that the beam size should be smaller than this number. Okay, and the station can be used for SARS measurement in transmission mode using ionization chamber and fluorescence-yield mode using 19-element germanium fluorescence detector. And apart from conventional measurement, the sample can be heat up to 750 degrees Celsius with the heater cells or the sample furnace designed by the beamline scientist Dr. Chatri, like this. And this heating cell can use both in transmission mode and fluorescence-yield mode. Yes, the beam coming in here hit the sample, and the sample fluoresces here. And this is the window for the fluorescent detector to put up somewhere here, around here. And also they can do the in situ measurement on the electrochemical cells to study electrolysis of the sample. And they also successfully developed on the fly XAS scan. That means they can reduce the scan time from the conventional 15 minutes on the energy scan to 5 minutes per scan. And the next beamline is called time result X-ray absorption spectroscopy, or sometimes we call it the energy dispersive beamline because it uses bent crystal monochromator, and this crystal disperse the photon energy and at the same time focus the beam on the sample spot. And then the energy is dispersed, the transmitted photon is dispersed in energy and in space like this. So it can be recorded by NMOS linear imaging sensor. And because the setup like this doesn't need the photon energy scanning, is already taken care by the bent crystal. So the time for each measurement is very fast. The fastest the wave time is 25 milliseconds per spectrum or per scan, and they can heat up the sample to 600 degrees Celsius. And they have the gas reaction like oxygen, hydrogen, and also those inert gas. And they can do very fancy setup. And this is the heating cell or the sample cell, the cross section of it, designed by our beamline scientists. And here you see it consists of cartridge heater at the end, at the bottom, and the thermocouple is here, and there's a gas inlet and outlet, and there's also X-ray window made of carbon, and there's insulator jacket. And this cell has been tested to see the change of cobalt foil to the cobalt in higher oxidation state when heating up in temperature. Okay, and just last week I went to this beamline to take a photo, and I was really stunned that it's very complicated setup. As you can see here, there's a chemical vessel going on here is with the heater, and there's some bubbling solution, and the gas just get into the sample chamber and out of the chamber. So I have no chance to ask around what they were doing at this station, but it seems to be a chemistry lab going on, and the in situ measurement is also done at this point. Okay, for the next beamline, the third beamline is the SUT-Nanotec-SLRI X-ray absorption beamline. It was participated by 3 parties: the university, Nanotech, and also SLRI. They are equally invent the budget to build up the beamline and run the beamline. So this beamline cover the quite low energy range. We call it the tender energy. X-ray energy is from 1.2 kV to 10 kV. And the optical design is very simple. I think it's the most simplest beamline for SAS. Just use slit to cut out the divergence of the beam from the bending magnet. And they use DCM typically for energy scanning. And they can do, at the end station, they can do transmission mode measurement using 2 ionization chamber here and here. And also for fluorescence-yield mode, they use 4-element silicon dip detector here. So this is 4-element detector, and this is the first ionization chamber and the second one. And also they can do various in situ condition, and they have a heating cell. They just designed this a new sample furnace recently, and it can heat up the sample to 1000 degrees Celsius. And the reaction gas is oxygen, hydrogen, and carbon dioxide. And they also have the inert gas in this for use with sample for the in situ measurement. And the last beamline is my beamline is the X-ray absorption spectroscopy. And here, the difference between beamline 8 and beamline 5 is that the beamline 8 use collimating mirror to make the beam more parallel. That means we have more flux for the end station, and we also use the double crystal monochromator for selecting photon energy. We have 4 types of crystal to cover energy from 1 keV up to 13 keV. And the beam size is quite large. It's about 13 millimeter by 1 millimeter. Okay, and the photon flux is about 10 to the 8 to 10 to the 11. And we have several types of detector. And here is our SUT station. And here, this is the ionization chamber for transmission setup. And this is, I think this is our old 7-element detector. And now we have, and this one is the 13 germanium detector. And we recently bought 13-element silicon diff detector. And we also design our electron-yield detector by in-house, and the cell is look like this, and we submit for Thailand patent already, and we got an application number. And this mainly used, this electron-yield cell is mainly used for sodium, magnesium, and aluminum KH measurement, as electron-yield at this eigenvalue of this element is very high, higher than fluorescent yield, so it's very effective. We have already tested. And for the 4 beamline, we can see that they are very productive, especially for beamline number 5 and beamline number 8. Altogether, they can publish, the user using the beamline can publish more than 60 papers per year. And the category of the sample, the major sample type that has been studied by SAS at SLRI is catalyst. And the second one is the energy storage material. And then the electroceramic, and also soil sample and environmental sample. Okay, I think I will break here to take questions.
Okay, very good. You do have a couple of questions, Wantana. The first one is, what fraction of users are from Thailand, and what fraction from other ASEAN countries?
I think it's about 10% or 20% from ASEAN, especially from Indonesia, Philippines, and Malaysia. We don't have any, and also Vietnam. We don't have yet any user from Myanmar and Laos and Cambodia.
Right. The next question is it true at beamline 8 that there is no radiation hutch? How do you maintain radiation safety at 13 keV?
That's a good question. But I walk around the beamline without hutch with confidence, you know, because we have a safety group that can do radiation survey, and when the beam on and the sample is inside, and so we monitor the scatter radiation, and then the readout from the dosimeter is quite low. It's as low as the background. That is because the tube, the chamber, the measurement is not in open air, you know. the measurement, we have the sample chamber, and the thickness of the chamber is made of stainless steel, and the thickness of the chamber is about 2 or 3 millimeter, and that is enough to shielding scatter radiation. And the next factor is at 13 kV, we don't have enough, we don't have high flux. The flux is about 10 to the 8. So the radiation is even lower. Okay.
So, great. You have a few more questions that I think are good questions. So why don't we move on?
Okay.
The next question is, how do you reject harmonics in the beam?
We don't actually, we don't have rejection mirror to deal to cope with this problem, right? But as I said, when we go up in energy, the flux drop very quickly. So higher for when we work at the higher energy, the higher harmonic disappear already because of the flux of the first harmonic themselves is already low. But for the low energy like 1 kV, we sometimes we have problem with higher harmonics. But anyway, even with higher harmonic, we can get a good transmission spectrum. Sometimes we got a peak of argon, argon excited at 3 keV, right? Sometimes we got the argon peak appears as 1.6. When we do aluminum KH measurement, it always gets in the way in that spectrum.
I remember that from the time that I measured data.
Right.
The next, I'm sorry, go ahead.
Yeah. You go ahead. I just go into small detail. That is okay.
Okay, so the next question is asking about your beryl monochromator crystal. This person says he is unfamiliar with beryl and asks, is it radiation hard or does it require frequent replacement?
That is a good question. So my comment, the first comment is that the beryl crystal is very expensive. We bought it from Saint Gobain, and the size is half of the usual size that we use for silicon for indium antimonide 111, but it costs like three times higher, and it not radiation hardness. We see it burned very. We see the burn mark very quickly once we use it. But I monitor the flux that it doesn't affect the flux or lower the flux that much. So we just keeping use this crystal for like 4 and 5 years now. I think it will last. And also we have cleaning with ozone. Every year we clean our crystal with ozone bombarding to clean up the carbon hydrogen layer. It's just the burn mark that made from carbon residue. So we clean up our crystal every year, including beryl.
Okay, so one last question for now. I see another question just came in, but I think we will talk about that later. Let me ask Matthew's last question. He asks, what keeps somebody from taking off a flange with the beam on? I think his point is about the end station being out in the air. Then somebody could interrupt the measurement that way.
We don't have any case since the first operation. We don't have any case that
You also
that
have staff at the beamline almost all the time with your users, right?
Right, right.
Yeah.
And we a little bit threaten them about the detector, how expensive they are.
Right.
And we don't allow them to modulate the setup.
Right.
So we train the user at the beginning of their beam time, and we have this very strict procedure they have to follow. How
Right.
to
Very good.
close the beam shutter and how to open it. It's just a few buttons on the computer that
Right.
are allowed for user to operate.
Okay, very good. We will have more time for further questions later on. Why don't you carry on for now?
Okay. Okay, so I will go on with a few interesting science paper. The first paper is about the zirconium-based metal organic frameworks used as a catalyst of the oxidation of benzyl alcohol to benzaldehyde. This benzaldehyde is very important and for the production of pharmaceutical drugs and agricultural chemicals, and also is used for perfume, production of perfume and anything else. And so the team led by Champa Thong and his team, they want to do the molecular engineering of the zirconium-based MOF. Here it has, because it has the zirconium node like this, and also it has the OH bond, that is hydroxyl bond that can be easily exchanged with the iron. They want to put iron 3+ in this node here. So the precursor is iron acetylacetonate, and they exchange the ligand with the OH bond here to anchoring iron in this node. This is the active side.
Wantana?
Yes.
Have you switched to a new slide yet? It still is showing break time for questions.
I did.
Why don't you try to switch back and forth? And if that doesn't work, you might have to stop your share and then share again. But try to flip the slides back and forth.
I flip it and you don't see it, right?
No, okay, so you should stop your share and then share again.
Share again. Can you see it?
Yes, now we see the MOF slide. Very good.
Yes,
Thank you.
Much better. Thanks.
Okay, so I will repeat again. Okay, so this is the MOF catalyst framework, right? And they want to insert the ion in this node. Yeah, it's a ligand exchange between the acetylacetonate change of a carbon hydrogen group and also the OH group of the original zirconium node, like this. Okay, so this is the active site for the oxidation of the benzyl alcohol to benzaldehyde, and this is very good catalyst because it doesn't undergo over oxidation to benzoic acid, and they don't produce the waste product after the reaction, after the oxidation. So it's very promising new type of catalyst. So what they need is to prove whether the ion is in the wanted side or the desired side or not. So they use SEN. First they measure SEN spectrum at the ion KH and compare with the several standard. And you can see on this slide that for the precursor itself, the iron acetylacetonate and the blue and the green spectrum here. So the energy is a little bit higher than iron 3+ in the iron oxide standard. This one, right? This is iron 3+ oxide, and but for the sample itself, it looks more similar to the precursor, even have the higher edge energy. And this is, I think, they conclude that this is due to its form complex, not like the oxide standard. Okay, and to even further prove the site, the atomic environment around the ion. So they took a XAS spectrum and do the Fourier transform, and this is the graph after Fourier transform of the data. And they use the atomic model shown in this picture here, and they can fit it with the theory. And you see the first shell iron bar here, iron bar with 6 oxygen. Here, this is the first peak. And the second one is the iron, oxygen, and carbon. Here, this peak. And for the next neighbor, they can even fit the peak bonding between iron and zirconium. So this is the structural model, and it agree with the experimental one. So they can prove that the site is correct. Here they can insert or anchor the iron into the active site, and the conversion factor for this type of catalyst is very high. It's about 99% conversion from benzyl alcohol to benzaldehyde. Okay, and the next the next research or the next topic, this group led by Hong Han and his team, they study olivine cathode for lithium-ion battery. And this is the experimental setup. The battery cell is here, and this is the beamline number 2. It used this energy dispersive setup. And so here is the assembly of the battery coil. The cathode is lithium iron phosphate, and here the anode, usually graphite, and they assemble the cell and put and insert the cell in the beam part like this. Okay, and they design the chart and discharge cycling like this, and also they have a relaxation time to study the in situ measurement. And here when the cell charge up, it changes from lithium iron phosphate, crystal lithium iron phosphate to iron phosphate. And when discharged, the cells, the cathode change from iron phosphate to lithium phosphate. And this has been known already for a while or before. So they do the in situ measurement to prove that, to confirm that. So during the charge here, C1, C2, C3, and C4 cycling, they can nicely see the oxidation state change from iron 2+ to iron 3+, charge up from 0 volt to 4.5 volt. And then during the discharging, so they reduce the voltage inversely, and the iron change from 3+ oxidation state to 2+ oxidation state. And the lower graph here show the different spectra, and is even clearly see that the oxidation state of the iron in lithium iron phosphate, which is 2+, has changed to iron phosphate, which is iron 3+. And further, they also study take the measurement during the relaxation. The relaxation means they drop the current to 0 and let the cathode relax by itself, and they take the measurement of the same, and they still see during charging, they still see a small change of its energy to higher energy. But for the relaxation during the discharging, it's very surprising that they still see the change of the H energy in the same direction, you know, as the charged one. Actually, they expect that it should be in the other way around, but the energy it keep changing into higher energy. So they think that this is caused by the decrease of FeO bond length, because there should be a metastable state of larger FeO bond length before the cathode change to its crystalline phase, either in form of lithium iron phosphate or iron phosphate. So the relaxation time is just happen over 10 minutes, and you can see this is the different spectrum. After 10 minutes, it's stable here, so it becomes crystalline after 10 minutes. And also here for the relaxation during the discharging process. Okay, and the next research I picked up is about phosphorus and sulfur speciation on soils, and we have many users from Europe, such as from Germany, from Sweden, and also from Australia, and recently a group from Japan. They want to use our beamline to study phosphorus, to get the phosphorus sense spectrum and sulfur sense spectrum in soil. Because why it is important in soil science to study these two elements? Because first, because phosphorus is primary plant nutrient and sulfur is the secondary one, and P and S stock in soil is limited, and usually phosphorus is bound to carbon in soil, and it can undergo chemical change due to the soil chemistry and soil condition and other factors. But phosphorus exists in numerous forms of phosphate in soil, and also similar to phosphate, sulfur can exist in several oxidation states, ranging from the reduced form like a sulfide, that is to minus oxidation, and up to sulfate, that is sulfur 6+, and the availability of S and P for plant depending on soil, P and S stock, and also speciation. And these two factors change with ecosystem succession. Okay, and also P's also can threaten water quality when they have phosphorus solute in water. They promote algae growing, and that create the water pollution, right? So beamline 8 produces high quality P and S KH sense spectra for determination on speciation, and our detection limit is about 100 ppm of total phosphorus and sulfur. We can get a good spectrum within 3 hours, I think. Okay, and this is a comparison to just to make sure that the people coming from abroad can get a good spectrum from our beamline. Yes, we compare with the NSLS or beamline of NSLS is already shut down. Yeah, the blue data taken for 15 hours, and beamline 8 only 2.5, use only 2.5 hours to get a much better signal to noise ratio in the spectrum, in the phosphorus spectrum. And also we compare the data with the APS beamline 9 BMB here on the same sample and the same measurement time, and we have a higher signal to noise ratio. So this gives confidence for user coming from abroad. And we have, that's why we have about 12 papers published already since 2018, and they are all international user. Here, study soil in different conditions, like cultivated organic soil, and also soil from Antarctica, and also soil sediment from Baltic Sea, and also the phosphorus that has that make water quality worse, and they try to study the phosphorus removal from domestic wastewater as example, as a good example. So I picked this one because it just published in 2019 by George Purcell and his team, because phosphate in soil has very numerous forms, so they build up a reference spectrum of important absorbed organic and inorganic phosphate binding form for soil phosphorus speciation. And this one show you one type. There are three main types of phosphate. Those bound with iron, and it has a different complex like this. And you can see that the spectrum is look quite alike, but when look closely at the pH region, you can see the pH peak. This is the characteristic of phosphate bound to iron, but for the post-H peak is quite the same. Here there's no, this is not distinguishable. And for this one is the representative of organic phosphate. So it has a chain, a six chain like this. It's very complicated atomic structure, and those also has a very complicated ferrihydride phosphate. This has very complicated atomic structure. And then the second group is the phosphate bound to carbon, and you can see it has already 1, 2, 3, 4, 5 types of them. And if look closely, carbon bound phosphate, it doesn't have a pH peak, but it has a shoulder, very distinctive shoulder peak here after the white line, right? And some of them has a small peak here before the broad absorption band around 2170 eV here. So this can be used to distinguish phosphorus species in soil sample. And the last group is the aluminum, is the phosphate bound to aluminum, and it already has lots of form here, and he has a measurement of them. And for aluminum phosphate bound, it doesn't have pH, but some of them has a distinctive small peak between the white line and the broad absorption band like this. So we can do a linear, we can do quantification of the phosphate species in soil using a technique called linear combination fit. It's based on least square fitting. So for example, this is X-metal data. It's just a soil sample, one type of soil, and they use all of these standards as a basis, and then the fit gives the component, the main component, to reproduce the data, X-metal data. And it seems that in this soil type, it's contain iron, mostly contain iron phosphate, and then the second one is the aluminum phosphate, and then the pyritic acid, which is organic phosphate. And for the different soil type, and you can see here, this is the hydroxyapatite, 60% composed in this soil sample. And the hydroxyapatite here, you can, at glance, you can just recognize this shoulder here. Just a characteristic of carbon about phosphate like this. And the second species is the iron phosphate with the small pH here, and then the pyritic acid. So using linear combination fit is very useful to quantify the phosphate species, and also it works well for sulfur speciation too. And here I will talk about this paper in particular. It's also by the same group of researchers, George Fraser and his team. He studied Antarctic soils and whether how are the phosphorus and sulfur status in those soil, and whether it depends on site condition and vegetation. So they sampling the soil at the Antarctica, and this is the site they are sampling here on the James Ross Island, which is near South Africa, the South Africa here, and South Africa is up here, like this, okay. And this is James Ross Island, and this is the sampling site. This is T1, T2, T3, 4, and 5, and they also sampling the site that has a vegetation, and this one on the Bury Hill side, and this, and also this one on the Cape Lachman. But I will, because I have limited time in my talk, so I will show you only the result from the T site. The T site, the parenchymal soil is either basalt or sandstone and sediment, marine sediment, like this. T4 and T5 is marine sediment. So they dig up the soil under the ground and study them. And here also are some photographs of the site of with vegetation. The vegetation is only limited to lichen, mosses, cyanobacteria, and algae. Because as you know, as we already know, Antarctica has a very extreme climate, right? So the vegetation is very limited. And one factor is very important is that there is no penguin or other birds in the James Ross Island. So they don't have a contamination from bird nutrients and so on. So here, this show you a spectrum from our beamline, and this is the phosphorus spectrum, sense spectrum, and the lower panel shows the sulfur sense spectrum. And at glance, you can see that here I recognize this shoulder. So I would say the T side, the side T3, it's dominated by carbon-bound phosphate, right? And this looks to me like aluminum phosphate. But to make sure that to be quantificative, they use linear combination fit like I described before for both analyzing on the phosphorus species and sulfur species. So here, this is their result. So you can, they can get the amount of calcium-bound phosphate and iron phosphate, aluminum phosphate, and also sodium and potassium phosphate and other types of phosphate here for each soil site, and also similarly for sulfur. This is they can differentiate inorganic sulfide, organic reduced form, and sulfur oxide, and moderately oxidized sulfur, including including sulfate. So they can do quantification of each species, and this is very important because they can relate the speciation and the quality and their quantity to the site condition factor like parential material on each side, weathering on each side, and also the factor of sea water, sea spray, and overwhelming flooding of sea level of sea water like this, and they can associate the change of appetite increasing with this one of these factors. So this is very important because the knowledge of PNS status will be used to predict the effect of climate warming on the important biological and chemical processes in Antarctica. Okay, this another break time for questions.
Yeah, Wantana, so we think since you're running a bit late, why don't you just go on and I will present all the questions at the end.
Okay, here the next one, the last type of research. Can you see it?
Yes, it advanced properly this time. Thank you.
Okay. So this is my own research. Personally, I really interested in studying cultural heritage material. So this is the first research, and we study ancient glass bead from the southern part of Thailand. It's the opaque red glass, and we took the measurement, the same spectrum of copper, because we found copper in this glass, and from glass chemistry, it's predicted that copper can give the red color if it exists in the form of metallic cluster or metallic nanoparticle. So here we took a measurement, and we found this is the beads, right? And we found copper foil signature here, copper foil characteristic that confirm the metallic form of copper in this glass. But also we found this peak that look like copper 1+ is occupied here, and this is the first derivative spectrum just to confirm it further. And here we also took the measurement of the on the XAS data. We got the XAS data and did the Fourier transformation, and then we fit it with two phases. The first one is the metallic copper, here the blue curve, and the copper 1+, the green one, and they add up and fit very well with the data. So from this analysis, we conclude we can get the percentage of metallic copper cluster on nanoparticle producing the red color in each glasses is about half of copper in metallic form and half in copper 1+. And copper 1+ doesn't give any color, is colorless in glass. Okay, and the second research is about the decorative glasses, and we got the the glass sample from the temple of the Emerald Buddha, which is the most famous temple in Thailand. And here the first set of the glass came from a pillar of this building housing the Emerald Buddha. And the second glass is the blue glass from this building housing the past king statue here. This is King Rama I statue. So we try to, the aim of the research is quite challenging. Not only studying the glass composition and coloring element, we have to reproduce the glass to its original color too. So here we start with the yellow one, and we found iron, lots of iron in this glass. Here the yellow contain about 7 to 9% of iron. but the colorless gas contain much lower iron content. So we took the same measurement, and this is the spectrum of the graph, and the edge energy line up really well with the iron 3+ in these two standards, the iron oxide 3+ standard and andesite. Andesite is a mineral that already has a that has a 3+ state of iron in it. Yeah. So we conclude that for the yellow color, it caused by iron 3+ dispersed in the glass metal. Okay. And also we also focused on manganese too, because in gas chemistry, manganese is facilitate the oxidation of iron from 2+ to 3+. So we study manganese same spectrum, and we see that the energy line up with manganese oxide. So we conclude that it is manganese 2+ in this gas, which give depend on the gas composition. Manganese 2+ can be colorless or can give a light purple color in this gas. But the content that we found for manganese in this gas is very low, it's lower than 1%. So we conclude that manganese help to oxidize the iron in this ancient glass or antique glass. And the next one is the blue glass. We found about 900 ppm cobalt in this glass. And also the second element, coloring element, is iron in this glass at 0.4 weight%. So we study copper, same spectrum, and we conclude that by seeing the edge energy, we conclude that it is cobalt 2+, because it line up well with the cobalt oxide here, with the dashed line here. So it's copper, it's cobalt 2+ that gives the primary color of the glass, make the glass blue color, in blue color. But we also study the yellow color undertone here, because we have iron in the glass too. So we check the oxidation state, and it is 2+. And we also synthesize or made the gas ourselves, just putting the same amount of iron in the gas, and it gives the yellow very faint, very undertone yellow color like this. So if we reproduce the gas with cobalt alone, we wouldn't get the blue color as the original one. We must add a little bit of iron, and it has to be in 3+ state to give the color blue color like this. And this color is called oriental blue, not the cobalt blue. This is cobalt blue, and this is called oriental blue, like the blue in Chinese porcelain. So with the knowledge of the composition, gas composition, and the coloring element and its oxidation state, we can reproduce the glass. And this one is the original glass from the temple, and this is the one that we reproduce in our lab using the knowledge from SAIN, combining quantitative X-ray fluorescence analysis. Okay, and the last one, I would like to end my talk. I would like to acknowledge a few people. They are SAS beamline manager, Dr. Claire, of beamline 1.1, Dr. Yin Yot, beamline 2.2, Dr. Pinit, beamline 5.2, and also beamline scientists, Dr. Shati, Dr. Wanvisa, Dr. Sujinda, Dr. Penkisha. So they kindly give material for my talk, and they are very supportive. So we work as a team, and sometimes we have problem with user, like especially for new user, they don't know which beamline to be used for their sample. So we have we work closely together and to make sure that the user will get a good quality of the data. Okay, so I think I thank you everyone for listening to my talk. Thank you very much.
So that was quite wonderful, Wantana. Thank you very much. We do have a couple more questions for you.
Yes.
So here's one that seems very important. You are asked, does SLRI have options of rapid access or mail-in?
Right. Just now during COVID situation, we have mail-in service.
So it's a new thing.
Yes, it's a new thing.
Cool. So, and if somebody wanted to use mail-in, how would they go about doing that?
It just they have to go through ordinary process, starting with submitting proposal, beamline proposal on the website. So submitting the proposal online, they can check for detail how to do so in the website of SLRI. It's slri.or.th. So once they submit the proposal, their proposal, we've got a review from our review panel, and if the proposal is accepted, and then they can send. They will be asked to send the measurement details and also the safety approval for the sample to be arrived at SLRI. And then once the sample arrive here at the facility, the safety people will check for matching to match the sample in the package and the list they gave us. And if it can be handled by safety equipment that we have, then the sample will be allowed to do the experiment to be measured at designated beamline. And our staff, so each beamline will have a team, scientists and also assistant scientists to help run the sample 23 hours a day. Yes. And some beamline have automatic sample changing, and they can program it overnight to get the data in the morning. Yes.
Okay, very good. Well, maybe you'll have a new customer after this talk. I have a few.
That's good.
Yeah, that would be very good. I have a few science questions for you from the science part of your presentation. Jerry asked, what is the typical concentration of phosphorus in the soils that you measure?
Okay, so it's the sample that we have encountered has a large range of phosphorus, total phosphorus concentration. The lowest one is 50 ppm, and that takes about 5 hours.
Right.
So we scan like one scan per hour, and we have 5 scan and then merge all of them to reduce the noise. But typically it will be around 500 ppm up to 1,000 ppm.
So then Matthew asks, when you are doing concentrated references for the phosphorus and sulfur edges, how do you manage the problem of overabsorption?
So use the standard that there's a paper about building up reference of phosphorus standard by George Purcell, right? So it seems that soil scientists they know how to do the measurement, how to prepare the standard. They dilute the standard to the same concentration of the sample range. So all the standards were measured in fluorescent mode. And there's even a paper coming out checking the cell absorption that depend on the dilution concentration level.
so not so much avoiding the problem of overabsorption as building a set of references that manage the presence of overabsorption is what you're saying.
No, not quite like that. So they try to reduce the absorption effect, say absorption effect, by diluting the standard, either with quartz, which is the main which is the main component in soil, right? And some also dilute with boron nitride, and they dilute it to like 1,000 ppm or even lower.
Right. So then Matthew just mentioned in the chat a good point. He says the concentration of a standard can still be low and still be subject to overabsorption if the particle size is large, which in this energy range is 1 micron or so. So that's a valid point. So hopefully your colleagues have thought about that. The final question, or at least the last one that's here in the chat right now, Jerry asks, does your work on glasses suggest how to replicate the methods used by the old artists?
No, the answer is no. So it just the information from sand and the composition just give you the idea how to melt the glass, like mixing those ingredients, those oxide in the glass. But it does give you any idea how to make the glass as thin as the original one. And also for being decorative, you have to coat it on the backside with reflective material, right? So we come up with a new method. So not like the old one, but we try to keep the composition as faithful as possible, as similar as possible to the original glass. So we try to reserve the recipe, the glass recipe. Yes.
So and the point is that you can faithfully reproduce the appearance of the glass. Right. Cool.
Right, but with the same coloring elements. That is our objective. Because, for example, for the blue glass, you can make glass in blue appear as blue color by several type of coloring elements. So like copper topaz also give blue color, and cobalt topaz also give blue color, and even iron topaz also give blue color. But the blue shades are different, right? So you have to reinvent it. And like I said, our oriental blue glass, it has to have a little bit of iron to produce that shade of blue.